This is the fourth lesson on Unit 5, Exponents. Specifically in this lesson, we'll be discussing characteristics of exponential relations. So just to start off with a bit of a review here, it says consider the following 4 equations and 4 graphs. Identify which graph represents each exponential relation. So what we're looking at here is that value, that base rather, that is being raised to the power of x. So you'll remember from our last lesson that we talked about a positive increasing function and a negative decreasing function. So remembering that our increasing functions were with our positive whole numbers and gave us that J shape, whereas our decreasing functions were fractions and gave us that L shape. So the larger the value, the steeper the curve will get, right? The greater increase or decrease depending on the direction. So we know that if we're looking at y equals 2x and y equals 5x, those are both positive whole numbers. So we know that those are going to be the ones that have that J shape, just based on that last lesson. So because C goes up steeper than D, we can assume that C would be 5 to the power of x because 5 is greater than 2. Okay, so just by process of elimination, that means D has to be y equals 2x. Okay, so we've labeled C and D. Now looking at A and B. And again, we know that these two graphs, A and B, are the ones with fractions because, again, they're making that L shape opposed to the J shape, which, again, is a negative decreasing function. So again, the larger the number on the bottom, the steeper that graph is going to be. So we can see that B is growing quicker than A if we are going up to the left. So that means that B has to be 1/5 to the power of x, and A is 1/2 to the power of x. So the next question says, what does each of the exponential relations have in common? So if we look at these graphs here, obviously, yes, they're all raised to the power of x. They have to be, right, to be exponential functions. But we also notice that all 4 of those lines are crossing at the same point, right? So they all have the same y-intercept, which is 0, 1. Okay, they're all crossing at that same point. Which exponential relation shows a growth relationship? So again, the growth is that J shape. So we know that would be C and D. And the decay is kind of that L shape, which is A and B. Let me go back to my color here. All right, so let's kind of just summarize some characteristics of exponential functions y equals a to the power of x. So the y-intercept is always going to be 0, 1. That's a 0, not a 6. There we go. 0, 1. Okay? And we saw that above. All 4 of those graphs crossed at that same point. The graph of an exponential relation does not have an x-intercept. Right? None of those graphs crossed our x-axis. They got really, really close to our x-axis, but they never actually cross. The growth decay factor is the base of the power, which is the a in y equals ax. For exponential growth, if a is greater than 1, the graph increases very slowly for negative x values and increases rapidly for positive x values. The graph is almost horizontal on the x-axis and approaches infinity on the right. Okay, so if I scroll back up here, we're looking at C and D for our growth. So when the x values are negative, we can see that we're slowly increasing. Highlighter here. We're slowly increasing here, right? And as we get to the positive x values, we start rapidly increasing. Okay, so on that x-axis, we can see that these numbers are approaching 0, right? It's almost horizontal. And on this side, we can see our lines are almost straight, right? They're approaching basically infinity, if we can think about that. Infinity is just the largest number. They're just going to continue to get larger. Okay, so the bigger the value of A, as we should know now, the quicker the growth. Okay, if we have, so what that means is y equals 100 to the power of x will grow faster than y equals 2 to the power of x. Oh gosh, that's a small eraser. Let's just back it up. There we go. Okay, exponential decay on the other hand. So decay occurs, as we learned in our last unit, or our last note rather, if A is between 0 and 1. Okay, so the graph is going to decrease rapidly for decrease rapidly. Yes, negative. Decrease rapidly for negative x values, and decrease slowly for positive x values. Okay, and again, if we look at that up here, we're looking at graphs A and B now. We can see that they're decreasing very, very rapidly on this part of our graph. But when we get to those positive numbers, that decay slows down, right? It's a less steep line. So the graph is almost vertical on the left and approaches horizontal on the x-axis. Okay, so again, we look, if this is a straight line, which it's not, but imagine it is, we can see A and B are almost exactly the same, right? They almost have the same slope. And if we look over here, we can see that the line almost becomes a horizontal line there on your x-axis. Okay, so the smaller the value of A, the quicker the decay. Okay, so 1 over 20 is smaller than 1/2. Okay, so that means the number on the bottom, if the number on the bottom is larger, then the number is actually smaller. So this is the first half of our note here. So mostly that just summarized what you learned in the last investigation. Okay, so an introduction to growth and decay, and this is just going to basically set us up for our next lesson. So obviously with all of our lessons, we're building on concepts as we move forward, but this unit specifically, we kind of introduced the unit or the topic in the lesson before. So this is an example of growth. So York region's population, P, is projected to grow until 2031, based on the relation P equals 610,000 times 1.029 to the power of n, where n is the number of years after 1996. So A is asking us to sketch the graph of this relation. So in order to do that, you did this in units before. This is just a matter of substitution. So it's telling us the number of years after 1996, which is giving us our n value, right? So all we have to do is plug in these values in this column for n to solve for the population. So I I have room, so I'll try to write it all out. So we're using that equation it gave us. And this time we're to the power of 0. Okay, we know from our exponent rules that anything to the power of 0 is 1. So this is just 610,000 times 1, which is 610,000. Okay, for the next one, you're doing the exact same thing, except you're subbing in 10 as your n value. And you guys would obviously have to use your calculator here. I've already done it. And you would just continue with that, subbing in the number it gives you for n to get your totals. And I think you get the process, so I'm just going to write in the numbers for the next ones. They're quite large, as you will see. Okay, and then once we have those points, obviously, looking at the graph we're already given here, we see that our number of years is on our x-axis. So these values are going to be our x values, and our population in thousands is our y value. So because it's in thousands, all you have to do is you need to take those answers that you got and divide them by 1,000. Okay, so you just are looking at basically the first the first 3 digits to plot those points. There we'll have 4, right? 4, 4. Okay, and then it's just a matter of plotting on our graph, right? So in the year 1996, or 0 years after 1996, rather, our population, we're going to plot it in thousands. So just above 600 there. Okay, next one, after 10 years, it's just over 800,000, somewhere in there. After 20 years, it's about 110,000. After 30 years, we're just over 14,000. And again, just try your best. It's not going to be perfect, right? And lastly, after 40 years, we're just over 19,000. It'd be somewhere in there, okay? And then obviously taking the time, trying your best to connect those dots with a curved line. Okay, so your graph should look something like that. So it says part B says, what is the p-intercept and what does it mean? So the p-intercept, it's really asking you for the y-intercept. Okay, so that is when x is 0. So when x is 0, y is 610,000. What does this represent? It represents the population in 1996. Right, because it's 0 years after 1996. What is the projected population in the York region in 2031? So to figure out how many years that is after 1996, we're just going to do 2031 minus 1996, and we will get 2031 minus 1996 is 35 years. So we're looking at 35 years on our graph to figure out what the population is going to approximately be. So that's this line here. I should use a different color. So at 35, we draw a line up on our graph and stop when we hit the line. Okay, and then we're going to draw a line over, and that will tell us approximately what the population will be. And again, this isn't a super accurate graph, so your answer might be a little bit different, but you could say the population is going to be approximately 1 million. Whoops, I still just have my straight line. There we go. And 600,000. And then we can just say after 35 years, or you could have said in the year 2031. Okay, the actual population at the end of 2009 was 1,032,606. How far off the projected population was the actual population? So 2009, we need to figure out how many years later that is. So 2009 minus 1996 was 13 years. Okay, so we're looking to see what our graph tells us the population is after 13 years. So you're going to be approximately here. We're going to draw a straight line. Mine isn't perfect. And then we're going to go over, oops, and see what the population was that we got. So according to my graph here, and again, yours might look a little different just based on how you plotted your points, but according to my graph, after 13 years, my graph predicts that the population is 850,000. Okay, but the actual population was 1,032,606. So in order to find how inaccurate that was, all we have to do is subtract. So the population prediction was almost 200,000 people off, which in the grand scheme of things, thinking about how many people this is, that's not too bad. Okay, so let's look at another example, this time an example that represents decay. So it says, a pressure reader is used to measure the sound intensity of a bell. Again, the context isn't super important, so don't get too caught up in that. What is important is the equation. So the relation P equals 200 times 0.5 to the power of T estimates the sound pressure P in pascals after T seconds. The graph of this relation is shown. So it says, what is the P-intercept and what does it represent? So looking to find the P-intercept, what we're doing is we are finding the point on our graph where we cross that y-axis. So that point is at 200. So in this context, what that is representing is the pressure at 0 seconds. All right, so at 0 seconds, our pressure of this bell is going to be at 200. So part B asks us, what is the sound pressure after 1 second? So again, we're going to use our graph to figure this out. So at 1 second, so that's here, and we're going to draw a line up until we hit it, and then we're going to draw a line over so we can see what that pressure would be. So at 1 second, we can see that it's at 100, and I'm just going to go through all of them while I have this straight line. So at 2 seconds, again, draw it till I hit the line, and then go over. So that's going to be approximately 50. And at 9 seconds, so that would be somewhere over here, right? So at 9 seconds, what we can say, because we can't really tell what the exact number would be, but we can infer that we know that a decreasing or a decay has a decreasing line where this blue graphed line is going to almost become a horizontal line, right? It's not going to cross that x-intercept or that x-axis. It's not going to have an x-intercept, but it's going to come really, really close. So at 9 seconds, it's going to be almost 0. And it's pascals is just a measurement, okay? So at 1 second, again, we found that the sound pressure is 100 pascals. At 2 seconds, it was approximately 50 pascals. So 1 and 2 were pretty easy. For that 9 seconds, you would have to infer a little. You'd have to remember that that blue line is never going to cross that 0 mark. So it would just be a very, very, very small number. So think about it as like 0.000001. It's not 0, but it's really, really close. Okay, so this is the end of our 4th note. We just have one more to go.